I have 50 resumes on my desk for one cloud architect role. Every single one of them lists AWS, Azure, and Zero Trust as skills. But when I get them in this room, 90% of them freeze when I ask, how do you actually implement Zero Trust across 3 different clouds without bankrupting the company? Stop memorizing definitions. I know you know what an S3 bucket is. I need to know if you can secure it when a developer leaves it open to the entire internet at 2 a.m. Today, we are doing the Cloud Security Gauntlet. I've taken the 30 hardest questions I ask during final rounds, covering Kubernetes, IAM strategies, serverless, and data sovereignty. If you want to move from cloud engineer to cloud architect, you need to master these answers. Hit like if you're ready to level up, subscribe so you don't miss the next mock interview, and let's get to work.
Let's start with design. How do you implement a Zero Trust architecture across a multi-cloud environment, AWS and Azure? Don't just give me the buzzwords.
Zero Trust isn't a product, it's a strategy rooted in identity as the new perimeter. In a multi-cloud setup, I focus on 3 pillars. 1. Unified identity. I'd centralize identity, using an IDP like Okta or Azure AD so we have a single source of truth. 2. Micro-segmentation. I wouldn't rely on flat VPC peering. I'd use a service mesh, like Istio or Linkerd, or cloud-native tools to enforce strict service-to-service authorization. Service A in AWS should only talk to Service B in Azure if explicitly authorized, regardless of the network path. 3. Continuous verification. We verify every request based on context, user location, device health, and risk score, not just the initial login.
Design a secure, highly available, and fault-tolerant cloud architecture for a global e-commerce platform. Where do you start?
I start with resilience and isolation. 1. Front door, global load balancer, like Cloudflare or AWS Global Accelerator, with WAF and DDoS protection at the edge. 2. Compute, auto-scaling groups across multiple availability zones in at least 2 regions for disaster recovery. Active-passive or active-active. 3. Data, a managed database, like Aurora Global, with red replicas in secondary regions for low latency and failover. 4. Security. I'd isolate environments, prod, dev, stage, into separate accounts, JAWS subscriptions organized under an organization unit to limit blast radius.
How do you balance security, cost, and performance when selecting cloud security controls for a startup?
It's about risk-based prioritization. 1. Native first. I maximize cloud-native tools, AWS GuardDuty, Azure Defender, because they are pay-as-you-go and integrate instantly. 2. Guardrails, not gates. I use service control policies, SCPs, to prevent expensive mistakes, like spinning up large instances, rather than expensive manual reviews. 3. Performance. I avoid inline appliances that add latency. I prefer out-of-band monitoring or sidecar proxies that scale with the app.
What are the key security principles for migrating a legacy on-premise application to the cloud?
The biggest risk is the lift and shift trap. If we just move a VM, we move its vulnerabilities. 1. Refactor for immutability. Ideally, we containerize the app so we can patch the image, not the server. 2. Decoupling secrets. Legacy apps often hard-code passwords. I would mandate moving all credentials to a secrets manager before migration. 3. Close the flat network. On-prem apps assume a trusted internal network. In the cloud, I'd enforce strict security groups to allow only necessary ports.
Describe your approach to data residency and sovereignty in a global cloud deployment, e.g., GDPR, CIPA.
Geography is a physical constraint we must architect around. 1. Region locking. I use organization policies to physically restrict which regions developers can deploy resources to, e.g., Germany only for EU data. 2. Data sharding. I architect the application to store user data in the region of the user's origin. 3. Tagging and encryption. We tag all data by classification. For strict sovereignty, I might use customer-managed keys, CMK, where the keys are stored in a local HSM, ensuring the cloud provider cannot decrypt the data even if subpoenaed in a different jurisdiction. When designing robust IAM in the cloud, my foundational principle is that identity is the new perimeter. In a fluid, software-defined environment, traditional network boundaries are secondary to how we manage human and machine trust. My first rule is the elimination of standing privilege. No human should ever possess long-term static programmatic access keys, as they are a permanent liability. Instead, I architect for identity federation and role assumption, where users authenticate through a central provider and assume short-lived, temporary roles that expire automatically. This ensures that even if a workstation is compromised, there are no persistent keys to the kingdom for an attacker to harvest. To ensure this scales without becoming an administrative nightmare, I move beyond traditional role-based access control, RBAC, and implement attribute-based access control, ABAC. RBAC inevitably leads to role explosion, where an organization ends up with thousands of unique, unauditable roles. By using ABAC, I leverage tags as the decision factor, creating broad roles where permissions are granted only when the user's attributes, like their project or department, match the tags on the resource. This allows the security architecture to scale dynamically. When the business launches a new project, we simply tag the infrastructure rather than rewriting complex IAM policies. Finally, I enforce a culture of admin moments rather than admin accounts through just-in-time, JIT elevation. No one, including the security team, should have permanent administrative rights. Permissions are granted only upon request for a specific time-bound window and are subject to peer approval and full logging. This logic extends to machine-to-machine communication through workload identity. By allowing microservices and serverless functions to identify themselves via their own metadata rather than hard-coded secrets, we remove the need for secrets to protect secrets, creating a self-healing identity ecosystem that is baked directly into the infrastructure. In a modern cloud architecture, hard-coding secrets is more than a mistake. It is a fundamental architectural failure. My strategy for securing credentials centers on the principle that an application should never possess a secret. It should only possess the identity required to request it. We achieve this by utilizing a centralized vault, such as AWS Secrets Manager or HashiCorp Vault, to eliminate secret sprawl across config files and environment variables. The implementation relies on runtime injection via workload identity. Instead of storing a password, the application is assigned a cloud-native identity, like an IAM role or Kubernetes service account. At the moment of execution, the application uses this identity to authenticate to the vault and fetch the credential directly into memory. Finally, to minimize the blast radius of a potential leak, I enforce automated rotation. By configuring the vault to update credentials every 30 days without human intervention, we ensure that any compromised secret has a strictly limited half-life, maintaining a resilient and ephemeral security posture. Federation means we don't create cloud users. We rely on our existing corporate identity, e.g. Active Directory. It improves security by, if an employee leaves, HR disables their AD account, and they instantly lose access to AWS, Azure, and GCP. We don't have to hunt down orphan accounts in every cloud console. Securing cloud storage is never about a single switch. It is about building a defense-in-depth architecture that survives individual configuration errors. My first move is to implement a global public access block at the account level to provide a failsafe against accidental exposure. From there, I apply a restrictive bucket policy that mandates encryption in transit via TLS 1.2+ and limits access exclusively to specific IAM roles or trusted VPC endpoints, effectively pining the data to our private network. To protect the data at rest, I enforce server-side encryption, SSE/KMS, ensuring that any attempt to upload an unencrypted object is automatically rejected by the storage service. Finally, to ensure resilience against ransomware or accidental deletion, I enable versioning and object lock. By using a write-once-read-many worm model for critical logs and backups, we create an immutable data layer that satisfies both compliance requirements and disaster recovery objectives. Kubernetes is complex. I secure it in layers. 1. Use a managed service, EKS/AKS, so the cloud provider patches the API server. Restrict API access to a private endpoint, Bastion VPN only. 2. Use minimized OS images, BottleRocket COS, and rotate nodes frequently. 3. Enforce. Prevent root containers. 4. By default, all K8's pods can talk to each other. I implement Calico Chalk Cilium to whitelist only necessary traffic, east-west traffic segmentation. We catch it, it deploys. 1. Developers see red squiggly lines if they write an insecure Terraform config using plugins. 2. I integrate tools like or in the CI/CD pipeline. If the code tries to open port 22 to 0.0.0.0, the build fails automatically. 3. In production, we monitor for changes made manually, ClickOps, that deviate from the IAC template.
Detail your strategy for data encryption at rest and in transit.
In transit, enforce TLS 1.2 plus everywhere. For internal service to service, I prefer MTLS, mutual TLS, so we verify identity alongside encryption. At rest, I default to platform-managed keys for general data to save overhead. For sensitive, regulated data, I use customer-managed keys, CMK, via KMS. This allows us to revoke the key and crypto-shred the data instantly if compromised.
How do you implement data loss prevention, DLP, in a hybrid cloud setup?
Discovery is step 1. You can't protect what you can't see. 1. Classification, automated scanning, like Amazon Macy or Azure Purview, to find PII in storage buckets. 2. Egress filtering, inspect outgoing traffic at the network edge, using a cloud firewall or proxy, to block patterns matching credit cards or SSNs. 3. CASB, implement a cloud access security broker to block uploads of sensitive corporate files to unapproved personal cloud accounts.
How do you integrate security into CI/CD pipelines? Shift left.
I don't want to be the Department of No, I want to be the Department of How. 1. SAST, static analysis, scan source code for known vulnerabilities. 2. SCA, software composition analysis, scan open source libraries for CVEs, e.g., log4j. 3. DAST, dynamic analysis. Test the running application in staging for exploitable endpoints. 4. Container scanning. Scan container images for vulnerabilities before pushing to the registry.
Securely design and implement serverless functions, Lambda Azure functions.
Serverless isn't secure by default. 1. Granular roles, 1 role per function. A Lambda that writes to S3 shouldn't have permission to read DynamoDB. 2. Code dependencies. Since we don't control the OS, the risk is in the libraries. Heavy SCA scanning is critical. 3. Input. Validation. Since serverless is event-driven, we must sanitize all event inputs to prevent injection attacks.
How do you perform threat modeling for a new cloud-native application?
I use Stride focused on cloud boundaries. 1. Trust boundaries. Where does data leave our VPC? Where does it enter the API gateway? 2. Data flow, tracing the path of a user's request through microservices to the database. 3. Identify threats. Can a user elevate privileges here? What if this queue is flooded? DOS. Is this SQS message encrypted?
Design a cloud-native SIEM and SOC strategy?
I prefer keeping gravity where the data is. If we are AWS heavy, I'd use centralized CloudTrail and VPC flow logs feeding into a data lake or cloud-native SIEM. I focus on automation, SOAR. If GuardDuty detects a malicious IP, a Lambda function should automatically update the WAF NACL to block it before a human analyst even wakes up.
Describe your incident response plan for a major cloud breach, e.g., credential stuffing.
1. Identification. Confirm the breach via logs. 2. Containment. This is key in cloud. Revoke the compromised IAM role sessions immediately. Isolate the affected EC2 instances. Move to a quarantine security group. 3. Eradication. Rotate all access keys. Patch the vulnerability. 4. Recovery. Redeploy resources from known good IAC templates. Do not try to clean a compromised server. Burn it and build a new one.
What is Cloud Security Posture Management, CSPM?
CSPM is our continuous auditor. It's a tool, like Prisma Cloud or Wiz, that constantly scans our cloud API against compliance frameworks, CIS, NIST. It alerts us to misconfigurations, like an unencrypted disk or a public database, in real time, often offering auto-remediation.
What is the difference between a VPC, VNet, and a private endpoint? Answer. A VPC, AWS, and VNet, Azure, are your isolated private networks in the cloud, your virtual data center. A private endpoint is a network interface that connects you privately and securely to a service powered by the cloud provider, like S3 or SQL database, using a private IP address from your VNet, completely avoiding the public internet. Best practices for securing APIs in the cloud? Answer. Treat APIs like the new front door. 1. Use an API gateway for throttling and rate limiting to prevent DOS. 2. Enforce strong authentication, OAuth 2 OIDC, for every call. 3. Validate all input to prevent injection attacks. 4. Use shadow API discovery tools to find undocumented APIs developers launched without telling security. How do you protect against common web vulnerabilities? OWASP Top 10 in a cloud WAF. Answer: I don't just turn on the OWASP Top 10 managed rule set and walk away. That causes false positives. I run the WAF and count mode first to baseline traffic, then I tune the rules to our specific app stack, e.g., if we run Node.js, I focus on JS injection rules. I also use the WAF for virtual patching, blocking specific exploits at the edge while developers fix the code. How do you ensure continuous compliance and auditing in dynamic cloud environments? Answer: you cannot audit a cloud with a clipboard once a year. I use continuous compliance tools like AWS Config or Azure Policy. These tools monitor resource configurations in real time against our compliance framework, like HIPAA or PCI. If a resource drifts from compliance, e.g., encryption turns off, it triggers an alert or an auto-remediation action immediately. What are the key principles of cloud security? Strategic. Answer: 1. Shared responsibility. Know what you own versus what the provider owns. 2. Defense in depth, layers of security. 3. Least privilege, minimum access necessary. 4. Automation, security as code. 5. Isolation, reducing blast radius. How do public and private keys work in cloud security? Answer: in cloud, we use them primarily for identity, SSH keys for accessing VMs, though we should move to SSM bastions, and encryption, asymmetric keys in KMS. The public key encrypts data or verifies a signature. The private key decrypts data or signs a request. The golden rule: the private key never leaves the secure storage, HSM. What is a security group in a cloud environment? Answer: a security group is a stateful, instance-level virtual firewall. It controls inbound and outbound traffic at the network interface level. Unlike a NACL, network ACL, if you allow traffic in, the response is automatically allowed out. Can you explain the shared responsibility model in cloud computing? Answer: the provider is responsible for the security of the cloud, hardware, physical data centers, hypervisor. The customer is responsible for security in the cloud, data, OS patching, firewall config, identity management. In PaaS and SaaS, the provider takes on more responsibility, like OS patching, but the customer always owns the data and identity. What is the importance of data encryption in the cloud? Answer: encryption is the last line of defense. If our identity controls fail and our network controls fail, and an attacker steals the hard drives or scrapes the data, encryption ensures they only get garbage. It is also a mandatory requirement for almost every compliance standard: GDPR, PCI DSS. How do you securely manage encryption keys, KMS HSM, in AWS, Azure, GCP? Answer: we use a managed key management service, KMS. We separate the key administrators, who manage the key, from the key users, who use the key to encrypt. We enable automatic key rotation, usually once a year. For ultra-sensitive data, we use a cloud HSM, hardware security module, to ensure single-tenant dedication. How do you securely design and implement serverless functions, AWS Lambda Azure functions, with event triggers? Answer: 1. Least privilege roles. The function gets a role that can only do what it needs, e.g., read from this S3 bucket, not all buckets. 2. VPC integration. Run the function inside a VPC so it can access private resources without going over the public internet. 3. Code scanning. Scan the function's dependencies for vulnerabilities before deployment.
There you have it. That is the difference between a junior admin and a senior architect. A junior admin fixes the server. An architect designs the system so the server doesn't matter. If you can walk into my office and answer these questions with that level of focus on business value, automation, and risk management, you're hired. If this video helped you prep, hit the like button. It helps the channel reach more professionals like you. And subscribe, because next week we are doing a deep dive into Kubernetes security, the hard parts. Drop a comment below. Which cloud service is the hardest for you to secure? I want to know. Now, go clear that interview.